Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software-Defined Radio with HackRF, Lesson 3, What is a Decibel? Now I told you at the end of Lesson 2 that we would be going over the homework from Lesson 2 in this lesson, but I decided to put that off for one more lesson so that we could take a diversion and talk about decibels. You've seen decibels a little bit on the vertical scale of the FFT plots that you've looked at in GNU Radio Companion, for example, and we're going to use decibels throughout this course, so I want you to be comfortable with them. And the reason I want to take a whole episode to do this is because I see people make mistakes with decibels all the time. Even people who think they know what they're doing with decibels, people who should know what they're doing, make mistakes, and I don't want you to make the same mistakes. So let's just take a little time and go over the basics of decibels and get comfortable with how to use them. When people first learn about decibels, they're usually told something like a decibel is a logarithmic unit of ratio. And they're typically given a definition, a mathematical definition, something like 10 times the logarithm base 10 of a ratio A over B, or they're given a definition like 20 times the logarithm base 10 of the ratio A over B. Well, no wonder people are confused. Let's forget all that. I'm going to tell you the two fundamental things about decibels that you need to know to understand them. The first is that 1 decibel is 1/10 of a bell. In other words, 10 decibels, or 10 dB, equal 1 bell. Now the other thing you need to know is what a bell is. And a bell is a description of the number of orders of magnitude, or powers of 10 of a ratio. So if a ratio is 10 to 1, that's 1 order of magnitude, so it's 1 bell. If a ratio is 100 to 1, that's 2 orders of magnitude, or 2 bells. If you want to put it in mathematical terms, I would say that the ratio A over B is equal to 10 to the n, where n is a number of bells. Let's do an example. Let's say I'm 2 meters tall. Okay, that's a bit of an exaggeration, but we'll go with that. And let's say my brother is a giant and he's 20 meters tall. Now, how much taller is my brother than me? Well, 20 meters over 2 meters, that's a ratio of 10 to 1. That's 1 order of magnitude, or 1 bell, and there are 10 dBs, or 10 decibels in every bell, so he's 10 dB taller than me. What if he's 200 meters tall? Well, 200 over 2 meters, that's a ratio of 100 to 1. So how much taller than me is he? He's 100 times taller than me. Or he's 2 orders of magnitude taller than me, so he's 2 bells taller, or 20 dB taller, because there are 10 dB in every bell. What if he were 2,000 meters tall? 2,000 over 2 is a ratio of 1,000 to 1. That's 3 orders of magnitude, so he's 3 bells taller, or 30 dB taller. Now you kind of see how this works. When we add a bell, we multiply the ratio by 10. Adding or subtracting bells or decibels is the same as multiplying or dividing the ratios themselves. And this is why decibels are handy. Now, one reason they're handy is they allow us to describe quantities that vary widely over many orders of magnitude. The other reason they're handy is that they give us mathematical shortcuts. They let us add or subtract instead of multiplying or dividing. Now, here's a trick that you should know. Everybody should know that 3 decibels is approximately a ratio of 2 to 1. It's a very close approximation. And of course, you know that by definition, 10 decibels is equal to a ratio of 10 to 1. Using those two things, we can actually compute all sorts of different numbers in decibels. So, for example, let's say my brother is 4 meters tall. Well, he's 4 meters versus 2 meters. How much taller is he than me? He's 2 to 1, or 2 times taller than me. How many orders of magnitude is that? Well, it's not obvious how many bells that is until you think about your little shortcut. A doubling is 3 dB. So we just kind of skip the bells step there and say, oh, that's a doubling. We recognize that as being 3 dB. Or I would say that he's 3 dB taller than me, or I would say that he is 3 dB mics in height. That's his height, is 3 dB mic. And it's important to designate that what you're relative to here. And this is one way to do that. A similar thing you might have seen before is something like dBm, which is a way to describe decibels relative to milliwatts. Now, what if he were, let's say, 40 meters tall? How much taller is he than me? Well, 40 meters over 2 meters, that's a ratio of 20 to 1. Or it's a ratio of 10 times 2 to 1. And remember, multiplying a ratio is the same as adding decibels. So from the 10, we get 10 dB. And from the 2, doubling, we get 3 dB. And we add these together. He is 13 dB taller than me, or his height is 13 dB mics. Okay, now what if he's only 1 meter tall? And I'm 2 meters tall. How much taller than me is he? Well, he's not taller than me, he's shorter than me, but bear with me here for a moment. If he's 1 meter tall and I'm 2 meters tall, then the ratio of our heights is 1 to 2, or you might think of that as 1/2 to 1. We're dividing instead of multiplying. And when we divide ratios, we subtract decibels. So he's negative 3 dB taller than me. Or you might say he's 3 dB shorter. But don't say he's negative 3 dB shorter. Say he's negative 3 dB taller. What's his height? What is his height in dB mics? His height is negative 3 dB mic. Now in this case, I'm actually 3 dB taller than him, and he's negative 3 dB taller than me. What if his height is exactly 2 meters, which is exactly my height? The ratio of our heights is 1 to 1, so how much taller than me is he? Well, he isn't any taller than me, is he? And if you think of it in bells, how many orders of magnitude is the number 1? It's 0 orders of magnitude. So he's 0 bells taller than me, which is 0 dB taller than me. And you would say that his height is 0 dB mic. So there are 3 things that people get wrong constantly with decibels. And I don't want you to make the mistakes, so let's go over them. The first is that they fail to tell you what the decibels are relative to. This is extremely important. If I were to tell you that my brother were 3 dB tall, that would mean nothing unless I told you he's 3 dB mics tall, or he's 3 dB taller than me. The second thing that people get wrong all the time is they confuse amplitude with power. Now, amplitude and power are 2 things that we're going to talk about a bit in this course. But for now, all you really need to know is that power is the amplitude squared, or it's proportional to the amplitude squared. This is where that discrepancy between the definitions of 10 times the logarithm base 10 of a over b, and that other definition 20 times the logarithm base 10 of a over b. The reason we have these 2 different definitions is because of amplitude versus power. And you don't really need to worry about it much as long as you're careful that when you're describing power, you only describe power. When you describe amplitude, you only describe amplitude. As long as you do that, decibels work out just fine. But if you mix amplitude and power together, then you run into trouble and you have to keep track of this complicated math stuff. The third thing that people get wrong is that they get their negatives wrong. So for example, what if they said a system has negative 5 dB loss? Well, If they're describing something that actually is lossy, then what they probably meant was that it had 5 dB loss, or they meant that it had negative 5 dB gain. This is similar to the problem of saying that somebody's shorter or taller, right? If my brother is negative 3 dB shorter than me, then he's actually 3 dB taller than me. Does that make sense? If he's negative 2 dB taller than me, then he's in fact shorter than me. It's a little bit confusing. You can see why people get this wrong a lot. You just have to be careful about negatives and double negatives. So, these are the things that people get wrong all the time. Before we finish, I want to go over an example of something that kind of shows why decibels are so useful and are commonly used. Here's an example. Let's say my brother is 2.512 times taller than me, and my mother is 5.012 times taller than him, and my uncle is 3.162 times taller than her. Now, how tall is my uncle? Or how much taller than me is he? Well, you could multiply all these out, but you probably need a calculator to do it well. Or it would take you a little bit of time on a piece of paper. But what if we were to rephrase this just in decibels? This same exact question would be, my brother is 4 dB taller than me, and my mother is 7 dB taller than him, and my uncle is 5 dB taller than her. How tall is my uncle? Well, 4 plus 7 plus 5 is equal to 16 dB. He's 16 decibels taller than me. And all we had to do was add in order to come up with that result. Now, if we want to know that result in the number of ratio instead of in decibels, then we'd take that 16 and divide it into 10 plus 3 plus 3, right? That's equal to 16. And we would say, oh, from the 10, we get a 10 multiplying by 10. From the 3, we get multiplying by 2. Remember, 3 dB is a doubling. And from the other 3, we get another doubling. So he would be 40 times taller than me, a ratio of 40 to 1. And if I'm 2 meters tall, then he's 80 meters tall. But most of the time, and this is part of the reason decibels are so useful, is that people don't even bother turning them into actual ratios. They just use a computation like this to describe a system in dB. You might have something like, maybe with your HackRF, maybe you have an application where you want to transmit a signal through a directional antenna some distance, and you connect the output of the HackRF. Let's say the output is at 5 dBm. Remember, that's decibels relative to milliwatts. And then you're going to connect it to a filter, a bandpass filter that has an insertion loss of 3 dB. Now, you'd actually want to subtract 3 dB because it's a loss. You're subtracting instead of adding. And then it goes through an amplifier that adds, let's say, 12 dB. And then you're running it over a long cable that has 2 dB of loss. And then you're connecting it to your antenna. So now you want to know exactly how much power there is at the antenna. Well, 5 minus 3, and then plus 12, and then minus 2. What is that? That's 12 dBm. See how that dBm over here ends up over here? Because all we did was change it by ratios, and we know exactly how much power there is at the other end of the connection. So this is a very common type of computation that's done in the RF world, and you can kind of see why dBs are helpful here, because we're constantly adding we're constantly multiplying or dividing these ratios, and so decibels allow us to just add or subtract instead. Now, you don't have to absolutely master decibels in order to participate in this course, but I want you to be a little bit comfortable with decibels and know that when you see big number in decibels, that's a tremendously large number if you think of it as an absolute ratio, for example. And even though you don't have to master dBs, you actually could master dBs. And there are just these important things that you need to know, like a decibel is a unit of ratio, adding decibels is multiplying, and then you need to know those little tricks. 3 dB is 2 dB, and of course, by definition, 10 dB is, 3 dB is a ratio of 2 to 1, and 10 dB is a ratio of 10 to 1. But you can actually completely master decibels if you want, and actually be good at computing any number of decibels in your head. And I'm going to show you a little trick for how to do that. And this is an exercise that I'd like you to do for the homework for this lesson. What I'd like you to do is make a table. And first, I actually want you to do this on a piece of paper. Write down one column on the left, starting with 0 dB, 1 dB, and then keep going. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and keep going all the way down to 30. Then I want you to make a column to the right, and starting at 0 dB, write down the number, the actual ratio. So 0 dB is, of course, a ratio of 1 to 1 by definition. And then skip down to 3 dB. What's that? Well, it's approximately a ratio of 2 to 1. And now skip down to 6 dB. That's 3 more dB, so it's a ratio of 4 to 1. Then go 3 dB further. That's a ratio of 8 to 1, of course, because we're doubling again. Now go 3 dB further. That's a ratio of 16 to 1, and you're starting to see the pattern here. Now, if you're a computer person, you actually have an advantage in learning decibels because you probably know powers of 2. And all you need to know are some powers of 2 to fill out this table. And after you've gone through all of these by threes, then take a look at this 10 decibels. Well, you know what that is. By definition, that's a ratio of 10 to 1. And then if you go 3 dB further than that, what's 3 dB more than 10 to 1? Well, it's a doubling of 10 to 1, so that's 20 to 1. And then if you go 3 dB further than that, that is a ratio of 40 to 1. You're doubling it again. You see how now I'm going through powers of 2 again, except now they're powers of 2 times 10. Now, if you look at the exercise of the homework assignment actually written on the web page, greatscottgadgets.com/SDR, I actually guide you through how to fill out this table, and I tell you a recommended order for you to go through and fill out this table. And I think you'll find, as you go through it, that you're able to very easily come up with a ratio for every single line in the whole table. And just by knowing some powers of 2 and knowing some simple rules about decibels, like what 3 dB is and what 10 dB is, you can fill out this entire table and compute any whole number of decibels and turn that into a ratio.
Isn't that a neat exercise? I hope you'll enjoy filling out the rest of the table, and once you do have it completely filled out, I would like you to think about one question, and I think you'll be able to answer this question by looking at your table. The question is, exactly how much error is there when you use the 3 dB approximation for a doubling? So think about that a little bit, and I hope I'll see you in Lesson 4 when we do go over the homework from Lesson 2.